Hello everyone. In this lecture we will be discussing about oscillators. As the name indicates, these are the circuits which generate oscillations. These practically start with noise and generate oscillations, and theoretically we will be saying no input signal is applied, but the output will be oscillations. So we will be seeing two types of oscillators. One is RC phase shift oscillator and another one is Wien bridge oscillator, and we'll be implementing these using our op amp. And more importantly, the oscillator circuits as a whole will have positive feedback. So we have been discussing feedback. Amplifiers, they use negative feedback so as to control the amplification gain, whereas oscillators have positive feedback. Okay, so we'll start with the criteria for generating oscillations. These are provided by Bark-Hussons. We call this as Bark-Hussons criteria. So the first criteria is, for generating oscillations, the feedback over the complete loop should be 0 degree or 360 degree, and the product of gain should be equals to 1. Sorry. So what this implies is, this indicates that we should have a summing signal, or our signals should get generated. If our signals are out of phase, this is in phase. If signals are out of phase, the wave will diminish and become 0. So our feedback over the loop should be 0 or 360. A beta equals to 1 indicates sustained oscillations. This is the product of forward gain and the feedback gain. If this is equals to 1, we will be seeing sustained oscillations, constant height, constant frequency. If it is greater than 1, we will have exponentially increasing oscillations, bad for our circuit. Less than 1, decaying oscillations, which are again bad or useless. So we have to compulsorily make sure that these two criteria are met, so that oscillations are started in an oscillator. So we'll try to implement our two types of oscillators, very interesting oscillators. We'll start with our first one, RC phase shift oscillator. Important terms: RC phase shift means we are going to use 3 combinations of RC for providing phase shifts of 60 degree each. Okay, so what we'll have is, we'll start with an op amp. Op amp is not a compulsion. Any type of amplifier is sufficient. So we know this configuration. This is a inverting configuration. Say this is RF, this is R1. These are our supplies. So this is our input signal, output signal. This configuration is inverting configuration, and it provides a phase shift of 180 degree. But for our oscillations to start, we should have a phase shift of 0 or 360. So we require an additional 180 here, which is provided by a network of 3 RC components. This is the network. Many variations are there, but this is the simplest one. So observe that we are connecting the output here, and we'll take the input from this point. So this is our RC combinations, which are going to provide 60 plus 60 plus 60. So overall we have 180 plus 180, 360 degree. These are designed in such a way that A beta is slightly greater than 1. Practically we don't keep it exactly equals to 1, it will be slightly greater than 1, and the circuit generates oscillations of F equals to 1 by 2 pi root 6 RC. Okay, so this is how RC phase shift oscillator works. Forward, this is A, this is our beta, so overall 360 degree, and A beta should be slightly greater than 1, or we can call equals to 1. This is our RC phase shift oscillator. So Wien bridge oscillator, we are going to use a bridge network for generating oscillations, in particular named after Wien. The bridge we will try to write first. Say we have a combination of RC in series, another combination of RC in parallel. We will call this as R1C1, we will call this as R2C2. On other two parts of the bridge we will have, say, R3, R4. This is our bridge. So the connection what we are going to make is, we will use an op amp in the negative configuration, inverting configuration. We will ground this, we will connect this here, and we will connect a feedback on the output part. So this is our Wien bridge oscillator. These parts are going to provide 90 degree phase shifts. So 180 and again 180 here, because our signal is on the negative terminal. Total again 360 degree. Once we have this, the frequency of the generated oscillations is given by F equals to 1 by 2 pi RC for a condition R1 should be equals to R2, R3, R4, and C should be C1, C2. This will be termed as R. So if we have a balanced network of this type, okay, sorry, these are not necessary. R1 and R2 should be equal, C1 and C2 should be equal. These are going to generate oscillations of frequency 1 by 2 pi RC. What we'll do is, we'll as usual run our simulation in every circuit app. We'll try to analyze the 60 degree phase shift here, plus I will assign some homeworks. Try to solve the numericals in the homeworks, and let me know if you get any doubts. Till then, happy learning, all the best.